All right, so we're going to talk about derived distributions today. We have a lot of engineering problems and equations that describe a relationship between some dependent variable usually y, right, is equal to some function of independent variables. And these are usually our x, xi, let's say x1, x2, x3, etc. I'll just give you a very simple example of the deflection d of a cantilevered beam. And so here's our beam. It's got a length, and then there's some sort of load that is applied to it, a point load. So our independent variables, we have L, we have the point load, we have the modulus of elasticity. I mean, we don't, whatever. You guys did this in, what do you guys do this in? Materials? You don't take materials? Solids, okay. And we have a moment of inertia, I. And some of these are pretty defined, right? The modulus of elasticity is going to be a function of the material. It's something we can measure. So the uncertainty in that's pretty small. Same moment of inertia is something we calculate based on the shape. The length is something we can measure. So well, obviously that leaves one thing, so the point load. And where that point load is applied could be a random variable. We could also say, well, this is something we measure in the lab. And so there could be, a somewhat of a distribution of those values. So it could be a uniform distribution that kind of looks like this. That's often a starting place we think of uniform distributions, or maybe there's something about modulus of elasticity that maybe it's a normal distribution, something like that, centered around some average value. So we'll say, what if E and P, so P could be the magnitude of that load, are random variables with their own distributions. So we can create a derived distribution for D as a function of the distributions of E and P. We're not going to actually define those right now, but just kind of setting this up as a conceptual example. So let's just do this in a very basic way. Let's say we have a function y is equal to g of x. And we'll actually write that out. So say y, we'll just pick a simple parabolic equation, 3x squared. We'll say x is a random variable, and y then is a random variable that is a function of x. And when our big Y takes on some value, little y, we can say that x, little x, takes on some value, which is the inverse function of y. And what is the inverse function? You've done this in algebra. We're just solving for x. So we take this, we solve for x. So x is equal to the square root of y over 3. So that's our inverse function, which is, in this case, a function of y. And I'm saying inverse, so -1 just means inverse, right? This is not like an actual raising to the -1, it's just a nomenclature. And g is our function of x, so the inverse function is a function of y. So if, y is equal to 12, then x is equal to square root of 12 over 3, which is equal to 2. So we know then we can basically map values of x, or we can take values of x and then map them onto y via this inverse function. So what happens if we want to figure out the probability? So probability that big Y takes on some little value y. Well, that's going to be equal to the probability that big X takes on some value, which is a function of y, that inverse function of y. Those two are related. And we're going to say in this case for a single root, just to be mathematically comprehensive here. We're not going to get into the negative series right here. So we'll just say we're going to define the probability space. So then we could write this out as a PDF. And the way we could write this out, we could say is the probability density function of y as a function of y is equal to the probability function x, in which we plug in this inverse function. So x is equal to that, and we're just plugging it into the PDF. So this is a PDF for x, and then we generate a PDF for y. So what we're going to do then is kind of go through the steps that will ultimately get us to this, what this equation is for any type of distribution and any type of equation, assuming we can get an actual solution for it. But as we often do, to get to a PDF, we'll start with the CDF, and we just did that for the exponential distribution. And I promise you, this is the last derivation of the distribution we'll be doing. Oh, kind of. Yeah, a little bit of a lie. When we talk about statistics, we're talking about the t distribution, right? Which is based on the z distribution for a sample. Anyway, it's just like this is like the last super mathy one, I promise. Right before spring break. What a jerk. Okay. But this is fun. I mean, I think this is really, really cool stuff. So we'll start with the CDF, and then we'll eventually end up with a PDF. So we can describe the CDF. So the probability that y is less than or equal to little y, that's the cumulative distribution function. And that's going to equal to the probability that x is less than or equal to that inverse function of y. And so now let's actually do the math here. So we'll write this as big F of y. So this is the cumulative distribution nomenclature. And the way we did that in the past is we said that is going to be some sort of integral from negative infinity essentially to y, or up to that value of x. So in this case, we're going to do the integral of our PDF for x is less than or equal to the inverse function as a function of y. So this allows us then to plug in this, usually it's like from, say, negative infinity to x, right? But now we're going to plug this inverse function in for x. So we can say negative infinity to g, the inverse function of y. Okay. And now we're going to do a little bit of a calculus trick, which is, I think, probably Calc 1. The change in variables. Yeah, so if we say that, I'll just give the quick little example here. So if we were trying to do this integral 1x times 1 minus x squared to the 1/2 dx, we say u is equal to 1 minus x squared, du is equal to 2x. Then we can sub those in, change the variables, and we can say that this ends up being negative 1/2 u squared, negative 2x, negative 1/2 u squared du, right? So the 1/2 cancels out this negative 2. We've already got the x right there. So that's the part of the du. And then this is our u. So we're just substituting in the variables to make a more simplified integral. So we can do that here. And in this case, we're going to say that, we can say that, x is the inverse function of y. And so I'll plug that in and we'll say that big F of y is equal to negative infinity to y. We have our PDF of x, in which we plug in that inverse function. And then we have the derivative of it. So that's this du part right here. So now we're just going to take the derivative with respect to y of g negative 1 y. Yeah. So, and I'll just erase this to kind of clean that up. So this is the PDF, and it's a little bit awkward and funky, or sorry, the CDF, right? And then if we take the derivative of that, we get the PDF, which would be so we'll just take the derivative of the CDF. And then we just, by taking the derivative, you take away that integral. So we end up with the PDF of x evaluated at this function, within this function, times the derivative of that function. So this is some calculus here. And what we're saying is we have a PDF of x. We're plugging in that inverse function of y into that PDF of x, and then we're multiplying by the derivative. And by doing so, because we just did all this calculus, we end up with a PDF of y. So this says PDF of y is equal to this. If you do the math correctly, then you end up with a PDF that will, have an area of 1 underneath it when you integrate it. So that's the fancy trick. But the last thing that we'll note is that we have to take the absolute value of this, because we could have, if y increases with x, so if y is a function of x and we plot y and x, if it looks like that, or if it looks like this or something like that, then this will be positive. The derivative will be positive because the slope is positive. But if the relationship is negative or nonlinear or whatever, then this will be negative. And so we don't want a negative PDF, right? We don't want negative PDF values. So that's why we'll take the absolute value of that. Okay. Let's just look at a quick example together. And I've got this posted on Canvas. Derived distribution example. This is actually the first part of your lab for this. I just give a reintroduction to what we just did, the derivation of the PDF and the CDF. And then the example we'll talk about is this equation right here. So we have a function that is given, that gives us a wave height essentially. So if you have wind blowing over a lake, it generates wind, or generates waves. And there's some properties of the lake that influence the height of the wave. So the height of the wave is z, that's in feet. And we've got some variables in there. F is the fetch. You guys know what fetch is? It's a word you're familiar with. Just like how long does the wind have over an open body of water? Kind of like a straight line. So a lake, the fetch would just be the longest length of the lake about some axis that you're interested in. The ocean obviously has an incredibly long fetch. That's why we have a lot of waves on the ocean. Lakes typically don't have much waves because they have small fetches. Yeah.
So would you want the direction of fetch to be in line?
Yeah, and so for example, this particular equation is used to evaluate wave heights for reservoirs. And so if you're building a dam on a reservoir, how much freeboard do you need above the high water elevation so that waves don't like wash over it or cause erosion or something like that. So if you're, maybe you're going to put some riprap on the side of the dam, this would be a design equation for that. And so in which case, maybe you've got a windrose or an anometer, and you've got some information about wind in the direction of the fetch of the dam has this distribution, right? So maximum wind speed. So F is just something you can measure from the lake. We won't treat that as random. D is the average depth of the reservoir in feet. And so wind height is a function of how deep the water is. And then we've got V squared. So V squared would be the wind speed in miles per hour. You probably have to slice that up a little bit more, maybe like the maximum wind speed over 12 hours or something like that, right? So you probably need a duration for that. So what we can do with this example then is we'll take this basic equation, and I think I'll kind of have this side by side. We'll do it together. So here's our equation. And then we're given a distribution, a PDF for the wind speed. So that's going to be FV of little v is equal to 1 over V naught e to the negative V over V naught. And then we're going to say V is greater than or equal to 0. So this is essentially an exponential distribution that we just covered. And we have an average wind speed. So V naught is equal to the average velocity. So that's the one parameter that we'll put in there. And that's our rate parameter, remember. It's a little bit of a different formulation. You'll see, I think we derive the PDF as some parameter nu e to the nu t. This is essentially the same thing. So the first step is we need to find, so, okay, what are we doing here? We're going to find ultimately the distribution of Z. But first we need to find the inverse function of, so Z. So we can do that and we'll solve, let's see here. Okay, So we've got this function right here. This is what we're going to be solving for. And to do this, we're going to kind of simplify it. And we're going to say A is equal to the constants. So we'll take all the constants out and put them into 1. All right. So now we get Z is equal to AB squared. And then we get, with our inverse equation, A or B is equal to the square root of Z over A. So step 1, a little bit of algebra. We'll take the derivative of it. So dV with respect to Z is equal to 1 over 2 square root of AZ. So this is the negative 1/2, but we're taking the absolute value of it, right? Because we only care about the positive values here of positive probability. So we get that 1/2, and then we get whatever is in here to the negative 1/2 now, right? So this is 1/2, everything's a negative 1/2. Okay. So we did that derivation. Sorry, we derived that. Sorry, took the derivative of that. And now we're just going to plug everything in. So it's actually not too unbearable. So we're saying that the probability distribution of Z is equal to the PDF of V, in which we put in that that inverse function of Z, times the derivative So we go back up to our exponential distribution, which is right up there. We get e to the, now we're going to plug in whenever we have a v, right? So v is equal to this. So we're going to plug in e to the negative 1/2 square root of AZ. And all that is divided by v naught. And then we're going to multiply everything by, oh, sorry, I'm supposed to put the actual inverse function in there. That was I put the derivative in there. Okay, so negative the inverse function, which was right here. Right here, sorry, here's the inverse function. So square root of ZA all over V naught, and then times the derivative, which is 1/2 square root of AZ. Okay, a lot of things to keep in track, but we're plugging in V right here, and then we're plugging in the over DC right there. So if we simplify all that, we end up with f of z is equal to 1 over 2 v naught square root of AZ times e to the negative z over a all over v naught. And this is for z is greater than or equal to 0. So this ends up being our PDF for z. It's a little bit of algebra, a little bit of calculus there. And what does that actually look like? Then we can actually plot these. And so I give you an example of plotting these in R. Here's a plot for z. So z is as a function of v, just a parabolic equation. Here is our PDF for velocity. It's the exponential distribution. So it decays exponentially. And then the distribution for z is really looks very similar. Obviously, it's different with the different units, but we have now a PDF of our wave height. So what this can tell us then the probability that we'll have a wave height of 2 or 4 or 6 based on that wind distribution. So that's the power in this, that you can get a probabilistic formulation of some engineering question or application based on the underlying uncertainty or underlying probability of your variables. Yeah.
So is everything underneath one, just make sure?
Yeah. Yeah. So if you were to take this derivative, or sorry, integrate this from 0 to infinity, you get 1. Yeah. Based on all this math that we did.
Is the E the denominator, or is that multiplied?
Yeah, and I can write this out a little bit differently. It's just printed out here, but we'll,
So say like C is 0, it's 0, that does.
and I guess if we want to be super good at that, then we'll do that. All right. Okay, so this is our derived distribution. We derived it from an equation and a different probability distribution. Is this the exponential distribution? Not exactly, but it's close, right? It's something like the exponential distribution. It's just derived from it with a different equation. Let's talk about a couple more things real quick, and this will kind of cue you up for the lab. And we can calculate the mean and variance of functions of multiple random variables. So say we have a function y, it's equal to a function of many random variables, x1, x2, x3, all the way to xn. So each one of these is a random variable. Obviously, we're going to have trouble coming up with an analytical solution for multiple random variables, but we can calculate the mean and variance of them. So the expected value of y, or the mean of y, which we'll denote as mu of y, is simply equal to the function evaluated at the means of each of those variables. And this is a first order Taylor series approximation. So if we take the means of all of our random variables, the mean wind speed in this example, we plug it into the function, then we just get the expected value or the mean value of y. That's pretty obvious, right? So a very simple example, Q is equal to V times A. Then the expected value of Q, and say we did this in our hydraulics class. Did you take hydraulics with Rosanna? No. Okay. She'll do a lab kind of similar, and you'll use this error propagation. Will you take that class, or are you in a different track? Okay. So we do this in hydraulics. We take we have an area in that flume. We take a velocity measurement, and the velocity is a time series, which is a little bit variable. So time, velocity, because of turbulence, right? The flow is going to be, the velocity rate is going to go up and down. So if we take the mean velocity from this time series, then we can just simply say A is something we measure. The uncertainty is not that great unless the water elevation is changing a lot, but we'll say A is not uncertain. And then we'll say just multiply it by the mean velocity. So that will give us our expected value. Now the variance is a little bit different. Variance of y, which we'll denote as sigma squared y. This is equal to, or approximated by, sorry, the sum of each of the individual standard deviations of our x's, of our random variables, squared times the derivative of those. Sorry, the derivative of the function evaluated at the values of those. Okay, so d of dx of g and then all of this is squared. So what we're doing is we're taking the derivative of g xi with respect to xi. And then we're plugging in the mean value of xi, or whatever value we're using there. And so if we want sigma y, just the standard deviation, then we're taking the square root of all that. And note that we can't get rid of these squares here because we're doing a summation. So it's going to be sigma x squared times the derivative of the function evaluated at x squared plus the next one if there's multiple variables. And this is very similar to our propagation of error formula that we derived in hydraulics. So you'll see this again. And it'll just come to you so quickly. It'll be so natural. And then so just an example of this would be, say we have someone give me an equation. We're gonna do impromptu. This always goes well. Bernoulli's equation. Okay, so we have the head loss is equal to P over gamma plus V squared over 2G plus Z. Which one of these? So this is for head loss and pipe flow. This is not really, oh, sorry. This is just the energy. Let's do energy, just say H. So which one of these variables is going to be have a distribution, an uncertainty to it? Okay, so we'll say velocity. We'll say velocity follows normal distribution or something like that. So we can have mean velocity, and we can have a sigma velocity, right? So velocity follows normal with v mean, and we'll say sigma v. So to calculate, so first the expected value of h is simply going to be, we'll plug in, our mean values for all these. So, okay. But assuming these are not uncertain, the pressure we have fairly certain, that elevation is pretty certain. So we'll just we'll keep those as non-random variables. And then we can say the standard deviation of h is going to be equal to the square roots of, and we'll do this. We'll say first we'll have these are going to be, because these are not uncertain, the sigma, so we'll say sigma p is equal to 0 and sigma z is equal to 0. So then we don't need to take derivatives of these, right? So first we'll find the derivative of h, so dh with respect to v is equal to, we'll treat these as constants so they go away. So we just get 2v over 2g. Is that right? So v over g, that's our derivative. So now then we just plug in sigma v squared times v over g, and then we put in a mean value from that. What's that? Yeah, it worked out nicely. But say p wasn't certain, and p had its own, is just say positive, then we would say sigma squared p, and then we would just do this would be, then we'd have to bring in that term, right? Because that would be something. So, well, I don't know actually, because we would treat these as constants because we're plugging in values. So yeah, in this case, we would just get sigma p times 1 squared, since this is just a function. So these would be treated as constants, right? And then the last thing I'll say, and then we'll say happy spring break, is the relative uncertainty. This is something that we talk about in the lab. What is the contribution to uncertainty in H of these two terms? So that's a question you might ask, and that could be like a percent type of thing, right? So what is the relative uncertainty so we'll just say, okay, so we'll say the proportion or percent of total uncertainty in H from, in this case, we added P back in, so we'll say from V and P. Well, we know we can calculate a total uncertainty. So this is we'll just say this is the total uncertainty or total variance. So this would be our denominator, right? If we want to do the proportion. And so all we need to do then is say what is each element. And so we can take each of these elements out. So we'll just stick with variance and we'll say the derivative, let's say sigma xi squared times the derivative with respect to xi, g of xi. Squared all over sigma y squared. And so you can do this for each xi. So in the case of this little example, we would say sigma v squared times v over 2g squared all over sigma h squared. And this would be the percent of uncertainty by v, and then sigma p squared times 1 squared over sigma h squared would be the percent associated with the uncertainty in p. So we're just dividing by the total uncertainty or the total variance. I think you get a different number if you divide by the standard deviation. So just keep that in mind. Okay, that is our lecture in a nutshell. Take a look at the lab after spring break.